Hey everybody, this is going to be a quick one. We're going to talk about something called absolute convergence and a couple other related terms. And this is really just setting the stage for what's coming next. We need this for the next couple of tests that we're going to talk about after this, the root and the ratio test, which are going to be pretty vital to us. So we'll do this pretty quick. It's a pretty straightforward idea. So first, the definition, we will say a series, the sum over a sub n, is called absolutely convergent if the series made by the absolute value of its terms is convergent. All right, so if you can take a series and take the absolute value of its terms and make it convergent, then we call it absolutely convergent. So let's just do two quick examples. For instance, let's look at, let's take this series, -1 to the n, 1 over n cubed, okay? Well, this is an alternating series, right? And we won't go through all of the steps, but it's an alternating series. The terms are positive without this alternating part. The limit of 1 over n cubed is 0, and it's clear, I think it's pretty obvious, as n gets bigger, these things get smaller. So it actually satisfies all the conditions of the alternating series test, and this converges by the alternating series test. But let's also note, if I take the absolute value of these terms, all that ends up happening is, I guess I should have put in limits. All that ends up happening is we get rid of this negative part, right? The ones where, for any of the terms where -1 to the end is negative, it becomes positive anyways, and when it's positive, it's just a 1, doesn't do anything. And this series converges, right? It's a p series where p is greater than 1, and we know that this converges, right? So what we would say is that therefore the series is absolutely convergent. Okay, so in this case, it was both convergent and absolutely convergent, okay? But notice, absolutely convergent is a stronger statement. The series itself happened to be convergent, but its absolute value is also convergent. This is not always the case. Let's make a quick comparison. We've already done these, so I'm not going to spend too much time on them, but if I look at the series, let's say -1 to the n, 1 over n, this series converges, right? This was another alternating series test that we've actually done in a previous video. But if I compare this to the series, its absolute value, right, which just gets rid of the negative here, this diverges. Okay, so sometimes we take the absolute value, we still get something convergent, sometimes we don't. Okay, and so we can't just count on, one doesn't imply the other, I guess is what we should say. Being absolute, being convergent doesn't mean you're going to be absolutely convergent. Here's a great example, though we will see it works in the other direction in just a second. There's a word for this when we have this situation. We call this conditionally convergent. In other words, we say a series, the sum over the a sub n's, is called conditionally convergent if it is convergent, but not absolutely convergent. Okay, so you can be convergent like this one, but not absolutely convergent. Okay. However, here's maybe the key fact of this whole thing. We have a theorem. I'm not going to prove, it's in the text. If a series is absolutely convergent, then it is convergent. So if I know that, let's go to another page. If I know, in other words, if the absolute value of a series, right? If we take the absolute value of the terms of a series and this converges, then the series on its own converges, right? This is another way to say exactly this statement, right? If you have absolute convergence, then you have regular old convergence that we started this about. Again, it doesn't go the other way. You can have things that are conditionally convergent, meaning they do converge, but they do not converge absolutely, okay? Let's just do one example of where this kind of a thing might. The biggest place we're going to use this is in our next two rules. I'll do this in another video called the root and ratio test, where it turns out to be easier to look at the absolute value of certain kinds of series and just get any of the negative stuff out of the way. It just confuses things. And so we'll often be taking the absolute value anyways, and then we'll know if we find out that this absolute value converges, then the original series does. That's 90% of where we're going to be using this. However, we will once in a while see things like the following. Let's look at the series n equals 1 to infinity of sine of n cubed over n squared plus 1. Okay, so that's what we're going to examine. Let's take a look at a picture of this. Let's look at a graph. So let's see, where are you? All right, here's a graph of that situation. So I've plotted this series, right? Meaning, you know, at each integer, we get a point whose y value is the term of the series. So for instance, this 0 point, this point here, whose y value is 0.4207, that y value is the sine of 1 cubed divided by 1 squared plus 1, right? And then this value here at 2 is the sine of 2 squared divided by 2 squared plus 1. So one thing to notice about this test is it's not exactly alternating, right? We see there's 4 positive terms in a row, then there's a negative term, then a positive, there's a negative, positive, 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 negative, there's a few negatives over here. So it kind of goes up and down above and below the x-axis, or it doesn't alternate in a regular way around positive and negative. And so we can't use the alternating series test here, right? If it alternated nicely, this would actually fit pretty well into the alternating series test because, let's go back to it, right, this denominator is going to get rather large. So we're not able to use the alternating series test here. However, we can make the following claim. Let's consider the series made out of the absolute value of these terms, right? And we can make a pretty simple argument. This is always going to be less than or equal to 1 over n squared plus 1, right? Why is that the case? Well, sine is between 1 and -1. The absolute value is going to get rid of the negative anyway, so we can really, the absolute value of sine is going to be between 0 and 1. So we're taking 1 over n squared and multiplying it by something between 0 and 1. We get something smaller than it or equal to it in the cases where the sine of n cubed is equal to 1. Okay, so this part, so this is, I think, easy enough to see that this is true. And this is also pretty clearly true. We're adding 1 in the denominator, so our fraction is smaller compared to this one. Right? I think it's also pretty obvious to say these things are all positive, right? Greater than or equal to 0. Okay. So now we've got our series, the absolute value of our series is less than 1 over n squared. Recall, this series converges. It's a p series, right, with p greater than 1. Therefore, our comparison test tells me that this converges, right? Just write comparison test, right? Because I'm comparing it to another, remember our comparison test, we had positive series where one was always less than the other one. Then if the one so our series was less than a series that converges, we must converge, okay? Which means, therefore, again, the original series converges. Right? Because of this theorem that we just had about absolute convergence. So I'll just write absolute convergence here as my rationale, right? That if the absolute value, I don't have a good word for that, if the series made up of terms of the absolute values of our original series converges, then our original series converges, right? In other words, this statement here. We looked at the absolute value of our series, the absolute value of a sub n, that series, and we can conclude that the original series converges because of it. Okay, so there's a nice use of this absolute convergence. Okay, we'll come back with the root and ratio test soon.